Hello. In today's lecture, we're going to examine how chance variability can be estimated and used functionally in the regression model. We're going to cover a variety of topics related to the root mean square error for regression and go over several examples that will help us really get a full understanding of the use of error in the regression model. Briefly, the goal of regression is to explain why variables vary. It helps us quantify the relative importance of any particular variable. In particular, we are generally interested in quantifying the importance of the predictor variable on helping us predict an outcome variable. And as we'll see in today's lecture and today's topic, that we are also need to focus on not just predicting the outcome variable, but then we know that because we know that chance variability is always going to play a role in sampling, we can't get an exact prediction. We can only get an estimate. So we need to also estimate what we expect the chance error to be. An important thing to keep in mind as we're going through the RMS for regression in the next couple sections is that when you're going along the regression line, with as the x variable increases by 1 standard deviation, the y variable will increase by r standard deviations, where r is the correlation between x and y. This works because r is a pure number, as is the standard deviation. So we can get this very useful estimate, and we'll apply this idea in some other contexts too. The regression method uses the correlation coefficient and in several different areas, and we're going to look at some examples of how the correlation is instrumental in various aspects of the regression model and in measuring error in regression. What I've done here is just, these are just the boxes in chapter 11. And the reason I've popped them out here is because I want to help you think about how you might, if you wanted to make more concise notes that aren't just examples, or if you're flashcards or various other ways to, study or review on the go, I would suggest if you're going to take particular pieces out of the book, take the things that are in boxes. I know I've presented some formulas, but trying to memorize those formulas or any formula that we do isn't really going to be helpful to you in this class or in the real world. In the real world, you're very seldom, if ever, going to be asked to recall a formula. You'll be asked to understand what it means to do a procedure, or to understand procedures that someone else did. Even if you were doing the statistical procedures yourself, again, you're going to use a program like Excel or probably SPSS or something more sophisticated, and not be, you could look up any equations you needed, but you probably wouldn't need them. So the real focus should be on the concepts, and they're always in these boxes. One other point about this boxes that I wanted to give you a little study tip, which is that sometimes you might find yourself in your reading a little bit thinking, what is going on here? Like, I'm reading, but what's the point of this section? And if you're at that stage, go back to or beyond to look at the boxes that sandwich whatever area you're in. Go back and look at the box that, the most recent box you read through to remind you of the most recent major point that was made. And then look at the next, scroll down to the next box and see, okay, where's this all going? And then go back to where you were reading. And I think it will probably help it make a little more sense. So we use the root mean square error in regression to help us figure out how much actual values will differ from the predictions. And again, this is just allowing us to estimate the overall size of the differences between the actual values and the predictions, because chance variability is always playing a part here. So we can't, and if we knew the exact value of chance, we wouldn't need to estimate error. But we can't ever know the exact value of chance. We just estimate it using the method that's the most appropriate, that gives us the best estimate of the chance error in our sample. And that's what we're doing with the root mean square error in regression. In the first section, we're going to estimate the overall size of the differences using the root mean square error. And we're going to see some nice similarities between the distribution of the error and other topics that we've looked at, in particular, the normal distribution. And in that vein, the root mean square error is to the regression line as the standard deviation is to the average. So you have a normally distributed variable, you can get your average, and then the standard deviation gives you an idea of the spread of the data around the mean. The RMS error gives us an idea of the spread around the regression line. This is different, just as an aside, which we will look at more later, but this is an analogy between the regression line, the RMS error and regression line, and SD to average, which is different than looking at the SD of either the X or Y variables alone in the regression equation. The RMS error is different and more precise than those because it takes both of the variables into account. And we'll look at that. But first, we're going to do a little activity. So just as a fun way to help us see how we can get some chance variability in sampling. Let's say we were taking samples from among these rocks. We take sample, we get rocks, and then all of a sudden we get a sample that has an owl in it. Oh, chance variability. Just looking at this, you might not have seen that there was anything here but just a wall of rocks. But when you look closer, there's variability, and we will unpack this idea even more in our next unit, which is after the next exam in chapters 16 to 20 or so. The idea that repeated sampling and the meaning within finding an owl among the rocks. Here's another wall of rocks. You can see, okay, we could take lots of samples here, but eventually eventually we will find an owl. The point is not that owls look like rocks, just these owls do. But to help us remember, there's always chance variability there. You don't necessarily know what it is going in. And right now we're looking at the actual data. So we can see, oh, this data point, this is not a rock, it's an owl. But when you're looking at a summary like the regression line, it's giving you, it's always telling us the predicted values for Y for each value of X. So the prediction would be this spot is probably a rock. It just happens to not be sometimes. That sometimes is our chance error. So when we are predicting the error, we look at the vertical distance from the line. So that vertical distance could be above or below the line, and that it's important to remember that the line itself is always the prediction line for y based on each value of x, or the line that best fits the predictions. So when we get the RMS error, it helps us see the connection between the prediction error and the distance from the line. So it's helpful to think about this as it's distributed. So the RMS error tells us how far typical points are above or below the regression line. And to help us understand that, we can see that if we take the regression line and map one RMS error above the line and one RMS error below the line, that will contain 68% of the points on the scatter diagram. Similarly, if there are two RMS errors above the line and two RMS errors below the line, we've got 95% of the points within these two RMS errors. Now, this should be ringing a bell with you back to the normal distribution, because when we were looking at the normal approximation, remember how we learned that within one standard deviation above the mean and one standard deviation below the mean, there contains 68% of the population. Furthermore, within two standard deviations above and below the mean, we've got 95% of the population. And so this is pretty much the same idea happening here, except that instead of just looking at one variable, we're looking at two variables together. And so we're looking at y on x, not just looking at x. So that's why we're not just looking at one strip here, we're looking across the line. Although, of course, we will look at strips in just a moment. Let's think about an example for a moment. Let's say you needed to predict the weight of a man. You just said, hey, there's a random man. You need to predict his weight. If you get it right, you win, let's make it motivating, $1 million. Okay, well, you want to get it right. So your best guess should be the mean, whatever the mean weight of men is. For, let's assume we're in the US, since we are right now. So you get the mean weight of men, but that's really not very precise. I mean, the mean weight will be 50% of the population, but there's also a 50% chance that you'll be wrong if you guess the mean just looking at weight as the one variable. But let's say now you get a new scenario where you're predicting, again, the weight of this randomly selected man, but you're told his height. Now, knowing his height is really useful because you know that taller people generally weigh more. As height increases, weight increases. So if you know this man's height, you can say, okay, well, then I would, I can make a new estimate for the range that I would expect his weight to be in, and then choose the mean of that range. And since we now have a scenario where we've got a predictor, height, and an outcome, weight, we're looking along a regression line and we're saying, okay, we know that his height is at this point. So based on height, we would predict that, there's 68% probability that his weight would be between one root mean square error above and below the regression line. And so it gives you a much better chance of guessing correctly. And we're going to unpack that more in just a moment. But why not just use the standard deviation of y, or why not just predict based on y? Well, if we just are looking at y, our weight variable, then the standard deviation of y just tells us how far above or below the horizontal line. It just tells us above and below just based on y, but the standard deviation of y isn't taking into account the x variable. In order to get the x variable in the error expected as we move along the x axis, we need to add in another idea, which is the root mean square error for the whole regression. And it's important to remember that the units for the RMS error are the same as the units for the variable being predicted. I think we can skip that example. We've got more examples coming later. So when we compute the regression, the root mean square error, we know that the root mean square error is going to be smaller than the standard deviation of y. How do we know that? Well, because we just discussed that y is going to give us a bigger error term because it's not taking x into account. When we can take x into account, we get a better prediction and a smaller error. A worse prediction is going to have a bigger error in it too, generally speaking. And when we use the regression line to predict the points, it helps us get closer to the actual points, as you can see based on these diagrams, than just the horizontal line through the average of y. And we know that the root mean square, sorry, it looks like my formula didn't render properly here. The RMS square is smaller by the factor square root of 1 minus r squared. Now, just as to help map this onto you for you in some other ways, these are not just random. It's not just random that we've put r squared in here. R squared is its own statistical procedure itself. It's called the coefficient of determination. It tells us how much of the variability in y is accounted for by x. You don't need to know too much about it at this point, but suffice it to say, there's good mathematical logic here for why this works. So we know that the RMS is smaller than the SD by this factor. But so if we want to, and so if we want to know the RMS error of the regression line for predicting weight from height, we need to use this factor and then multiply it by the standard deviation of y. So we end up with a formula for the error that looks like 1 minus r squared times the standard deviation of y. And notice that we've got the regression, we've got R back in the mix again. We're revisiting here, we've got R again. And this is the third time that R has come into the overall regression story. First, R described the clustering of the points around the line relative to the standard deviations. You remember that in chapter 8. In chapter 9, we looked at how the average value of y depends on x. So associated with each one standard deviation increase in x, there's an increase of r standard deviations in y. This was a primary concept in chapter 10. And finally, we've encountered in the error term, we know that R determines the accuracy of the regression predictions vis-a-vis the formula for the root mean square error. One final point is that we talked a lot about predicting the y variable based on x, predicting the weights of men based on their heights. Men in the US from whatever time point of this period. Yeah, chill. Yeah, you. Sorry. Okay. So when we are predicting, we're using data that we've obtained from a study like this to predict our outcome variable based on an x variable or based on a predictor. We have to, it's so important, absolutely essential to keep in mind that you've got that your sample came from a particular population. So you really cannot extrapolate beyond the population that your sample was taken from. So we sampled, we've talked a lot about this data from the heights and weights of men in the US. Well, we cannot use those data to predict the weights of women in the US, right? We also cannot use those data to predict the weights of men in the Philippines or even probably in Canada. You might think, well, what's so different about Canada? There's tons of things different between the US and Canada. We may be adjacent to each other, but they've had universal health coverage for years. They're probably much less obese than Americans, or at least notably less. Even if they're not, we cannot assume that they would be. So we're not just talking about a population as being in the US, we're talking about a population as whatever your defined criteria for a sample was. It just so happens that the data that we've been looking at are from a US population level survey. So here we've got some problems for us to just take a quick look at. And you can see that we're just looking at identifying the RMS error in this first one. The law school finds a relationship between LSAT scores and first-year law scores. Note that the relationship is not very high, R equals 0.6, so it's just a really moderate relationship. And the admissions officer uses the regression line to predict first-year scores from LSAT scores. This tells us this is a real cue in here that this is a regression problem. Not just the fact this is in a regression chapter, but anytime a problem says you want to predict an outcome based on a predictor, you want to predict scores, this should cue you to thinking about regression. Regression, we only have a real small number of procedures so far, and only one thing that includes prediction, and that's regression. And really, we're only going to have one topic that uses prediction in this way, and that's regression. The RMS error of this regression line we're using to predict scores is going to be equal to 1 minus r squared times the standard deviation of y. So we know it's not 5 or 10. It's got to be one of these two. And we can see that if y is our first year score, the standard deviation is 10, the RMS error for the line must be this option. If we choose one of the students at random, and you have to guess his first year score without being told his LSAT score, you would probably just use the mean the average first year score. We would guess his average first year score would be 65 because that's the most common score. We'd be right half the time. But if we can use the predictor, we can look at our root mean square error and see that, and we could get a more precise estimate of our error. Oh, the root mean square error for just this first part, would be here. We're just, guess it's first year. We would still have the same root mean square error because we don't have his LSAT score. I guess it's not really clear if we have the other LSAT scores. I guess we assume we have all these data here. Okay. So if we were to repeat parts A and B and use his LSAT score, we could get the prediction by just using our formula for predictions of y on x. Y equals m times the value of x plus the intercept. Or since we don't have that, we would use alternately the standard deviation method, where we know that for each standard deviation increase in x, there's an increase of r standard deviations in y. So we could find out how many standard deviations his score is from the mean, and then get the z-score for that number. That's the standard deviation, the number of standard deviations, not his absolute difference from the mean. And then multiply that by r, and that would tell us how many standard deviations above or below the mean he would be on the outcome variable. So we keep talking about the RMS error. This is the same. This is our prediction error. It's also called the residuals. It's very commonly called the residuals, so it's important to know this term. I mean, you definitely will encounter it when reading journal articles, especially because regression is extraordinarily popular right now, not just like right now, 2017, but in this whole era of science. We love regression. So you see it everywhere. And it's very common to plot the residuals. When you plot the residuals, it means you're taking the scatter, you've got, instead of just your scatter diagram with the regression line, you instead replot the residuals so that you got a symmetrical diagram where the heights are equal, and you can then see the spread of the residuals. And there should be no clear pattern in the residual plot. If there is a pattern, that's a sign that regression is not really appropriate for those data. And it's important to keep this in mind because the most essential thing about doing statistics is choosing the appropriate test given the data. Just being able to compute a regression doesn't help you if you don't know when to do it and when it's appropriate not to do it. So looking at this, I've given you here this figure with the regression line residuals in a theoretical sense, and now here in our familiar height and weight data. And you can see how there's no clear pattern of the spread of the residuals around the residual line. If we could see a clear pattern, then it would not be appropriate to use regression. It's a test for the appropriateness of regression. And what would it look like if our residual plot had a clear pattern? It might look like, there's a curvilinear relationship in particular, or, that's not the only pattern you could see. You could see one where there's a clear pattern so the spread is not even. Let's think about spread a little bit more. So we can break down our scatter plot in our regression line, the whole thing, into vertical strips, so that instead of looking at everything together, we look at just a small portion of our data, and that enables us to get a more precise prediction. Before we do that, let's all learn how to say this word, homoscedasticity. It's scary. They maybe prefer football shaped in the book. I'm going to prefer homoscedasticity or homoscedastic because there's a Q inside the word as to what it means. Homo means the same. They're saying it's the same. Scedastic is referring to spread, but you can use the homo and hetero terminology, which you probably already know means same and different, to help you be a mental cue to you that homo something means that we're looking at if this is a homogeneous, if there's a similarity in the spread. And I'm going to help you learn to say this word. It rhymes with elastic. So if you want to say homoscedastic, first say, you can do it right now at home, say elastic, homoscedastic. Elastic, scedastic. Elasticity, homoscedasticity. So once you realize it rhymes with elastic, I think that makes it a lot easier to say. We can all say elastic. So here we've got a scatter diagram on the left that's homoscedastic. It's got an even spread about of the points within each of the vertical strips. And we're showing, for example, 2 vertical strips. The first strip is in solid lines, and the second strip, higher on the distribution, is in dashed lines. When you look at these, just the data from these 2 strips plotted next to each other, you can see them on the diagram on the right, that for one, each strip only includes the scores that were within that strip. So the solid line strip has scores from 58 to, technically they have a range there, but it's just looking at this strip of predictions. These are the sun's height that are on the spread. And we're looking at the spread of the predicted strips. So within that regular line strip, you can see in the regular line area on this histogram that sun's height within the strip is normally distributed. That's the key thing to remember here, that the outcome is normally distributed within the strip. And you can see that there's a very similar spread. These are statistically the same. They're both normally distributed and a similar spread. in the dotted line strip. So our dashed lines, you can see those have a normal distribution as well, and they are at a different place in the distribution of y because they're from a different area of the scatter plot, but they're both showing us a similar spread. When the scatter diagram is heteroscedastic, then the regression method is off by different amounts in different parts of the scatter diagram. And we just can't use the RMS error to give us an accurate measure of the error. It gives us a sort of average error across all the different x values. How is that problematic? Well, a heteroscedastic scatter diagram is going to show a different spread for each of the variables. So if we were to encompass it in a shape, it might look like this approximately. So you can see there's maybe a lot more spread at the higher values, less at the lower values. Could go the other way, but the point is it's not got the characteristic football shape of the heteroscedastic or the homoscedastic scatter diagram. I've included this problem by request. You too can request problems for inclusion in lecture. Just reach out to me. As you know, you can always reach me by text or phone. You can text me anytime you like, and just send a quick text to say, hey, can you include this in the lecture? And I'll be happy to do it, or whatever else you need. And so here we have it. Let's see, and this is a great problem to look at too. Here we've got a figure with a scatter diagram for the ages of husbands and wives in Indiana. The data are from the March 2005 Current Population Survey. And the vertical strip here represents the families. Let's look at our vertical strip, where what? The age of the husband is between, well, it looks like 19 and 31 years of age. So this is just a strip here within there. And let's think about the options based on this information. We've got these options for to fill in the blanks, and I'll just walk through these. Think about them as I'm going through them. The average age for all the husbands is going to be about, it'll be about the middle of this range from 19 to 31. From these options, it must be about 25. And the standard deviation, what would you think? Is that closer to 1 or 5 for just this strip here? Yeah, it could be 5. If 5 was our standard deviation, then we're just looking now at average age. So if 5 was our standard deviation, then we might expect to see some more variability in here. Oh, I was just double checking with the book on this, and this is a great reminder for us, especially on the eve of an upcoming another exam. yes, it should be 50 because this is asking us for the average age of all the husbands. You really must read closely. I just went and saw the strips and continued thinking about strips. So the average age for all husbands is about 50, which is, yes, that's true. We can see that here. Yeah, that looks right. The SD is about 15, which makes more sense. And if we look at the average age for all the wives, or would we expect that to be? About 50 again, because we're looking across the whole distribution here. And if we're just looking at the correlation between the ages of all the husbands and the wives, we can see here that it's certainly much higher than 0.25. Even 0.5, that's still a lot more spread. 0.95 makes the most sense. This is, yep, we're just looking at the dots. We can see that because we only have these choices, 25, 0.5, or 9.5. And so just looking at these, we know that a tightly packed dots around a line like this represents a very high correlation. So from among the options, 0.95 is the best. Now, finally, this is the item I was thinking about. The families plotted in the vertical strip. So if we just look at within this vertical strip, then we can see that the average age for the wives, especially remembering we're looking at these options for our answers, it's got to be about 25. It's certainly not 50 or it's 15. So it's 25. And what do you think the standard deviation is here? Since we're looking at a smaller area, it's got to be a standard deviation that's smaller than the standard deviation for the whole distribution. So I'm just looking at this and I can see that the average age is 25. And if the standard deviation is, say, 15, then I'd be going up by big jumps here. But I know that within one standard deviation, there should be about 68% of the population. So when I'm just looking at the dots, I'm estimating the standard deviation based on the knowledge that, for one, 68% of the distribution is going to lie within one standard deviation above and below the mean. So I'm expecting 2/3 of the data to be within one standard deviation above and below. And there's another key thing to keep in mind, which is that with a normal distribution, generally 6 standard deviations is enough to encompass all of the data points. So that's 3 standard deviations above the mean and 3 standard deviations below to encompass the whole thing. And so if we look back at our average age for the whole scatter plot and say, okay, well, where did we come up with a standard deviation of 15? Well, 15 times 3 would be 45, and 45, our scatter plot is approximately, goes up to 80. It's maybe a little bit big, but based on the 6 standard deviations to estimate the range, but it's more likely that that's going to be too big than too small. So you might get all of your data within less than 6 standard deviations. But if it's more than 6, then you know that there's a problem. So why did I know that the standard deviation for the whole data set couldn't be 5? Well, because look at how many standard deviations there would be in the data. 5, 10, there'd be easily 10, 20, you'd have way too many. So that just doesn't make sense. So now thinking about the final part of D, yes, our standard deviation would have to be about 5 because within 5 years of 25, we've got most of, we can see that would be right about here, and this is just approximate, of course, and here, and that is in fact about 68%, maybe a little bit more, but it's certainly the closest from among the options. Among families plotted in the vertical strip, the correlation between the ages of the husbands and wives is about, what do we think? Is it going to be the same as the correlation of our overall data set? Well, yes, it will be the same as the overall correlation in the data set. Remember, these data are highly correlated. It's certainly not dramatically lower than the correlation in the whole data set. We might see that it's closer to 0.5 than that it's rather lower, I should say, than the 0.95. It's a somewhat lower as you get to the ends of the distribution because of attenuation. There's increased spread at the edges of the distribution. So we would expect it to be between 0.5 and less than 0.95. And let's just finish looking at this since we've got the whole example laid out here. The SD is computed for the ages of all the wives or the wives whose husbands are 20 to 30 years old. Which SD do you think is going to be bigger? The first one is going to be bigger, and this is a trend we've seen in lots of exercises where if you have looking at a larger spread at more data points, then you're going to have a bigger standard deviation than if you're just looking at a constrained region of your points. But when we look at B, the SD for the ages of all the wives and all the wives whose husbands were born in March, we would expect these to be about the same because while age could be related to the spread of the points, being born in March versus another month is highly unlikely to. So we're going to finish up on this topic of thinking about the normal curve inside a vertical strip. It's often possible to use the normal approximation when you're working inside a vertical strip, and there are some requirements for doing this. You have to have points that are normally distributed within the strip, and the strips themselves, the diagram has to represent homeoscedastic data. So here we have an example narrow strip, and within this strip, we can say, okay, we're going to constrain down our data to just looking at this narrow strip because I want to get a better prediction. So I know if I constrain that, I can get a new average, and then this new standard deviation, which is the real essential thing to use. The new standard deviation for just this smaller interval of points is helps us to get a more precise prediction. So we'll do the review exercises. We'll talk through some of those in just a moment. Let's take a little break first, and then we'll come back and look at some of these review exercises. Any questions about what we were just talking about? how do I get the SD by just looking at a bunch of dots? Again, Stephen, I can only do that because I'm keeping in mind that I already know things about the SD. I know that the SD is within that one standard deviation, let's say above the point, should have 34% of the dots and one standard deviation below. So one standard deviation above and below should give me about 2/3 of all of the dots. So I'm using that knowledge. That's how I'm getting the SD, and I'm not getting the SD, I'm estimating the SD. And there is a really essential difference between computing the standard deviation and just estimating it. So I'm just estimating it, and I'm saying here, well, is it probably closer to 1, 5, or 15? I know it can't be 25. That's ridiculous, because that would, there could only be, 4 standard deviations across this whole scale. And we know there should be about 6 standard deviations across the whole scale. If it was 5, then there would be 40 standard deviations across here. That's just not possible, approximately, again, because we're just estimating. Why is it useful to be able to estimate this? Because you'll find that if you're reading research, you often are looking at graphs like this, and it can be helpful to just say, okay, I know that this estimate should be about, just from looking at this, I know it should be approximately 3 standard deviations above the mean and 3 standard deviations below the mean. So I say, okay, if my mean is 50 and my points go up to 80, then that's a 30-point spread. Why not say the standard deviation could be 10? Well, it could be 10, but it's more likely to be closer to 15 than 5. 10 wasn't an option. Also, it's more likely to be a little bit bigger, because remember that spread of 6 standard deviations encompassing your data set, that's saying that within 6. So 6 might be, here and here. It still includes all of the points within it. Is that helpful, Stephen? Okay. I mean, the important thing is we're not just looking at a bunch of dots. We're looking at dots that have been plotted strategically based on formulas that are reliable and predictable. So you want to find the average within the strip. Let's see. Well, the average within the new strip is inside the strip. Your typical Y value is around the new average. The new average is probably pretty close to the regression line. And C3. Well, review exercises are already in the next set, the next mini part of our lecture. So we'll hit those. I don't have number 4 in there right now, but I can put it in during the break. Exercise set E, number 3. Let's see. I just want to pull up the one you're talking about for us. And maybe that's a good problem to look at to help us with your question 2, Sarah. Or Stephanie, I'm sorry, about finding the new average within the strip. So I didn't forget about you. I'm just, I'm hoping that you'll be a good example for us. Oh, no, because your question, Stephanie, is more from part 4. Okay. No, part 5. Let's see. Yes, so it should be an exercise set E2. So let's look at this. You wanted to do number 3, but it's from the same study as number 1. So let's do number 1. Pearson and Lee obtained the following results for 1,000 families. We've got an average height for the husband, 68 inches, with a standard deviation of 2.7 inches, and then an average height of the wife, we've got a correlation. Not a very high one. So what percentage of the women were over 5 feet 8 inches tall? Well, first thing we need to do is think about, okay, how many inches is 5 feet 8 inches? So convert your height of the woman to the units of the average. These averages are in inches. So we need this woman's height also in inches. I'm sure somebody can figure that out. Whoever gets it first wins a kitten, an adorable kitten. You don't have to take the kitten. But first step here, make sure your units are right. Just going to my notes on this problem. So 5 feet is 60 inches. 5 feet 8 inches is 68 inches. I hope you're alive out there. Okay, well, hopefully it's obvious how I came up with this woman's height is 68 inches. And now we want to know what percentage of the women were over 68 inches. Well, 68 inches, and we need some units here. Just a moment. Or not units. I need a space to write here. So we know that 68, our standard deviation is 2.5. 68 minus 63 is 5. So we're have a deviation of 5 above the mean. That's 2 standard deviations, because she's 2 SDs above the mean. So what percentage of women were over 2 standard deviations above the mean? Well, now we know that we're looking for 2 standard deviations above the mean. That's a z-score of 2, because the scores are in standard deviation units. And we already know that 95% of the population is within 2 standard deviations above the mean. Remember a normal distribution. And if we're at 2 standard deviations, this is 95%, which leaves a total of 5% for this part and this part here. Together, they equal 5%. So each half, this half is 2.5%, and this half here is 2.5%. So what percent is going to be over 5 feet 8 inches? About 2.5%. Your book says 2%. That's fine. About 2.5% would be more precise, but yeah, I'm sorry I can't actually refresh in this, or I would lose you from the session. But for the record, nobody got my height conversion, but I trust you all can do it. So the percentage is 2%. Of the women who were married to men of height 6 feet, what percentage were over 5 feet 8 inches? Now we're just looking at the women who were married to men of a height at 6 feet. So 6 feet would be 72 inches. So that's somewhat above the mean. We should actually do this. 68 minus 72 is going to be x minus x bar. No, we go the other way. Sorry. A difference of 4. We have a standard deviation of 2.7. So if we take 4 divided by our standard deviation, we can get our sorry, let me get my calculator. But you could win a great prize for volunteering some of these answers. Oops. Okay. Thank you. Yep, 1.5 standard deviations above, approximately. So yes, thank you, Stephanie. This is a little bit off, and I do apologize. I really did need that break a minute ago. Oh my gosh. Everything starts going off here. You got what Stephen got. Let me see what we've been writing here. Yeah, it's not 1.5. I didn't get the new average. I used the standard deviation method. I should use the new average method, remembering that now we're just within this one strip. So we're looking at the men who were married to women who were married to men of a height 6 feet. So we're just looking within that strip. And if we want to get the average for the group of men who are, were husbands that are 6 feet, then we are going to use the regression method. So we're going to take our standard deviation and multiply it by R. So we've got, start over here. Our standard deviation was 2.7. Let me lay this out better for you. So when we're just looking at this one strip, we're going to need to take our standard deviation and multiply it by the correlation. So, oops. So our correlation was 0.25. So we can take our SD times R. It's going to be equal to, oops, times our standard deviation of 0.27. And this is how we get our new standard deviation. Yeah, I know sometimes there's rounding and not. Generally, like on an exam, I'll calculate a variety of appropriate answers based on rounding or not. So don't worry about it too much in that respect, except for where I've given you a specific direction for rounding. Oh my gosh, chill out. So let's say this. Yeah, I know. I see, Stephen. It's not working right. I honestly, it's not really a big issue in the big scheme of things you're going to see about regression and need to do for the exam. And it actually wasn't the question that led to us doing this problem was about number 3, which you're right, it is totally different. How are they getting their new average and the new standard deviation? I'm sorry, it should be not R times, it's just the standard deviation. I'm sorry, I really need to go to the bathroom. 1 minus R squared times the standard deviation of Y. And if we do that, I'm sure we're going to come up with the target answer, not target answer, but the one that we know to be correct. The square root of, I wish this would give me some more space here. There we go. So if I'm just going to use a new page because it won't give me any more space. So, and this is what you should do. If you find yourself solving a problem down the wrong path for one reason or another, you're tired, hungry, you need to take a break, just stop. Don't try to figure out what am I doing wrong, etc. You know you're doing something wrong. Step back and say, okay, let me start again and do this the right way and recognize that I just copied the wrong thing from my notes. In this case, I'm sorry. Oh my God. 1 minus r squared is giving us r squared times the standard deviation of y, of course, is going to tell us the new standard deviation. Let's map this into a formula. 1 minus 0.25 squared times our big standard deviation, or for the whole group, of 2.7. And let's just work this out. 0.25 squared. Oops. So we've got 1 minus 0.0625. We can't forget our 2.7 here. So now we're going to get our square root of 0.93. And so this is going to give us now 0.9. Well, we are just a moment. I'm just doing calculations. It's hard to talk and do numbers correctly. Calculations at the same time. So we should be using the standard deviation as spelled out here for the y variable. The husband is the predictor variable and wife is the y variable. How do we know that? We don't. I mean, they didn't tell us that. Okay. I'm just deducing that. I mean, we know from having seen this example before that they have it plotted out in previous spots in the text as predicting height of wife from height of husband. So we're supposed to rely on that. That's to tell us that husband is X and wife is Y. Since we need the standard deviation of Y, we need to use the standard deviation of Y value here. Which is 2.5. I agree this problem is tricky. I don't think it's... So I used 2.7 because, again, I looked at the wrong spot. Like I said, I really need a break for a minute here. I transferred my numbers wrong. I was thinking that we were first looking at the percentage. It doesn't matter. I just was transferred the numbers wrong. It happens. Come on. Move it. Okay. Yeah, so after break, I think we should do problem 3. That's the end product here. We need a little break. It's time for a little break. Too much statistics melts your brain. But you always hear me telling you to take a break. Yep, I'm sorry. Like everyone else, I am imperfect. I'm mostly right. The key with stats is to catch it when you're wrong. or to recognize when you need a break. So we got our new standard deviation. This is how to get it, the new standard deviation. Finish this formula here. And I'll just confirm that for you. Shouldn't be 0.6 here. This is, oh, so 0.963 times our 2.5, it ends up giving us approximately 2.4 for the new standard deviation. Okay, so yes, after break we will revisit problem 3. We'll have an opportunity to do another problem that is in this same family of problems. So don't worry, we will revisit this momentarily.